Yeah, hi everyone. So I'm Anjita De, and I will be the TA for this course. I'm basically a Prime Minister's Research Fellow working under the supervision of Professor Shubhendu Bhasin in IIT Delhi. And I'm working on my research area is related to adaptive control. And for this 4-week course, I've been assigned as the PMRFTA to this. So I'll be going through the tutorials, mostly speaking about uh, how one can apply the adaptive control, and I'll be focusing initially on solving the assignment questions. So I'll just guide you all to show how it can be done, and later, if required, we can move on to solving extra application-based questions if required. Okay, so yeah, I don't know if you guys can, some of you can turn on your mic and just confirm whether you can see the screen when it's shared. Okay. Yes. I think any of you, Navendu, maybe you can tell me whether you can see the screen. Okay. Thank you. Thank you so much. So we will wait for just 2 more minutes to see if someone else joins, and then we will start. Okay. So maybe just a minute, let me open the OneNote. Yes. I hope I'm audible right now. Okay. Okay. Thank you. So may I just ask you all, like, did you guys go through both of the lectures, and what did you understand from the lectures? Which I think lecture 1 and 2 were uploaded 1 week back. You want to say anything? Anything about adaptive control? What do you understand by adaptive control? What do you understand by adapt? I think that's an easy question. What do you mean by adapt? Okay, but what do you mean by adapt? Hmm. Right. Yep, yep, that's correct. It means to change. Okay, so it's not syncing properly. Maybe just a minute. Still time to sync. Yeah. That is syncing very slowly. Easy. So let me just say, I think it's taking a lot of time to appear in the screen. So yeah, you were right. May I get to know your name? It's saved by Lou Pixel, so I have no idea. Okay, okay. So I need to actually give your attendance, so it would be better if I write down your names. Okay, okay. Thank you. So yeah, to adapt means to change to something, right? You need to change based on how do we change. So it need not be only a PID controller, like you said, with tunable gains. To adapt means that suppose you're the aircraft, say it's an aircraft which is flying, and then all of a sudden there is a wind gust that appears to which you don't know how to respond. So an adaptive controller will not only tune the gains, it might take many other kinds of decisions which we'll get to know throughout the course. Decisions based on which the flight will not topple over or there won't be any other accidents if it's designed to address those safety constraints. So that's what we mean by to adapt something. Okay, so it can be adaptation can be a variety of things. For example, if you're driving on a road and a person appears all of a sudden, and if it's an autonomous vehicle, that means it's driving on its own. So in that case, to adapt means to address the fact that a person is coming and I should not be hitting that person. Rather, I should be going around the person or wait until that person crosses the road. Okay, so that's what we uh, mean by a controller being adaptive in nature. And it's mostly seen that whenever we are applying the adaptive design to even a simple linear system, it turns out to be nonlinear. And hence, the course is named in a way that both nonlinear and adaptive these are related to each other very in a very close manner. So I think Professor Bhasin talked about autonomous and non-autonomous systems on the very first day, where by autonomous we mean that the system dynamics, whenever you're writing them, is not explicitly dependent on time. For example, if I say x dot is equal to xt, in that case, just taking a lot. My internet is quite slow. So if you have, I'll just say it. So if you have x dot is equal to x into t, in that case, the state will change. Where x is the state, it will change depending on how t changes. So if the time is changing, that will also hamper how your state is varying. Right, so that's a non-autonomous system. But if it's only simple x dot is equal to x, okay, if it's only x dot is equal to x, in that case, what you have is just an autonomous system. That means there's no variation with time. It only depends on what's the value of the state. Yeah, that's it. So the first one is non-autonomous. The internet is really slow, extremely slow. It's kind of slow, but let's try. Let's see how much we can do. Um, I hope you all have a pen and paper so that you can write what I'm saying. Okay, so that's about autonomous and non-autonomous systems. Now, what do we understand by equilibrium points or stability in terms of equilibrium points? So, this is another important topic that is required in solving the assignments. So, the equilibrium point is basically given a dynamics or given how a system states are evolving with time. Okay, so the equilibrium point simply says that at what point or at what value of the state will there be no further variation unless it's disturbed. Okay, so you should not be disturbing the state in any way, and then it stays there. Now provided it does not change even if there is a disturbance, then that means that's a stable equilibrium point. Okay, for example, if I have x dot is equal to x, here simply x is equal to 0 is an equilibrium point. What do we mean by an equilibrium point here is because, see, x changes while, so basically if you plot it in this way, this is your x, this is your dx dt. Okay, the syncing is very bad. Okay. So x dot is equal to x means df, the rate of change of x would be equal to x at every time. So if x is equal to 1, so dx dt is equal to 1 as well. So it would go up by 2 provided whatever is the value. If x naught, that means x at time is equal to 0, right? And then it would increase further. So if you take a curve like this, it would look like a parabola, right? So this simply says that provided you are at 0, that means if your x is equal to 0, then x dot is equal to 0 as well, right? X is equal to 0 and x dot is equal to x, which is equal to 0. So there is no further change. Dx dt is also equal to 0, which means there is no further change. So if you stay at 0, then you will always remain at 0 no matter what happens. So that is your equilibrium point. And in fact, it is a stable equilibrium point. Why? Because even if you perturb it very small, in a very small fashion, if you change it a bit also, it won't be affected anyways. Okay, so that's why we call it to be a stable equilibrium point. Now when we discuss about Lyapunov stability, by Lyapunov stability we always refer to the stability of an equilibrium point and not of a whole system. You can't say the system is stable, it makes no sense. You have to say that this equilibrium point is stable. For example, if you consider a pendulum, okay, so a pendulum, it's rotating in this way, right? Now it can just move on in this way. So if you increase the force a lot, it can keep moving in this very fashion. Now if you do not move it at all, then it would rest at this very position, right? So this is an equilibrium point. Similarly, if you can put the pendulums to be exactly in the opposite vertical position, then this is also an equilibrium point. Just like this one, this is also an equilibrium point. However, one of them is stable and the other is unstable. Why? Because once it's in this position with the ball at the top, if you move it even a little bit, like if you move it here, it will start to fall in this way. Or if you move it here, it will start to fall in this way, right? So this equilibrium point is unstable. But now if you just keep it in this resting position, if you push it here, it will again come back to this position. If you push it here, it will again come back to this position. So this is your stable equilibrium point. Okay, so I think based on this, we can just start with the assignment solutions. Do we have any doubts till now? Any doubts from anyone? I think there was another person who got added recently. Yeah, Bakuli. Okay. So if we have no doubts, I'll just move on to solving some of the assignment questions. Let's first start with the first question. So, yep. I don't know if you can see the screen. Can you see the screen for week 1 assignment 1? I don't think so. So, let me just read the questions, otherwise stop sharing. Okay, so these are the questions that we had. For the first question, can you guys tell me what would be the answer? Which of the following are true about the adaptive control? So the first option is set of techniques which automatically adjust itself in real time. And I think so it's quite understandable. This is one of the correct answers because that's what adaptive means. Then we have useful for only linear system analysis. So any idea about this answer? Yeah, so this option is wrong. Right. So this option is wrong. It can be applied to linear as well as non-linear systems. So then we have used to deal with system uncertainty and parametric uncertainty. And yeah, that's the correct option because that's what I said, right? Suppose the aircraft is flowing and then your wind gust appears. So that was something that you did not know. It's an uncertainty. And yet you can address this with suitably designed adaptive control. So option 1 and option 3, these are the correct answers. So now if we move on to the next question. Sorry. Let me just open it here. So which of the following is a non-autonomous system? And we have discussed this briefly here, that for a non-autonomous system we have T to be explicitly uh, dependent, right? So T appears. And for autonomous system there doesn't appear a T in the equation directly. So for example, X here varies with time, but we don't have T explicitly put in the equation like xt square or xt cube or x plus T. So that kind of expression should not appear. So here out of the options given, for the first one we don't have T appearing, so this is an autonomous system. Then for the second one we have a T. For the third one we have a T in e to the power minus T. And for the fourth one again we don't have any T explicitly written in the expression. So option 2 and option 3, these two, I can select, okay, these two are the non-autonomous system examples. Okay, I hope that's clear to everyone. Okay, thank you. So now let's move on to this question. So it gradually starts to become interesting. So consider the following system. We have x1 dot equals to 2x1 minus x1 x2, and x2 dot is equal to x1 square x2 plus 2x2 minus 4. Now which of the following, so this is a dynamics given to you, it's not linear, there are non-linearities in it as well because you have this x1 square term and x1 x2 term, right? So which of the following is an equilibrium point of the above system? You are given a system and now you have to find the equilibrium point, right? So what's the idea to find an equilibrium point? Like we discussed earlier, an equilibrium point is the point where it won't be changing anymore. That means your x dot should be equal to 0. I don't know if I can highlight it. So your x dot being equal to 0, this one x dot is equal to 0, is the concerned point of interest. So whenever we are trying to solve an equilibrium point problem, we will always equate the dynamics, the differentiation terms to be equal to 0, and then we solve for the value of the states, and that would give you your equilibrium point. And the next step would be, then we will analyze whether it's a stable equilibrium point or an unstable equilibrium point or a marginally stable equilibrium, so on and so forth. Okay, so okay, so this is our first question's solution. So we have x1 dot equal to 2x1 minus x1 x2, and x2 dot is equal to x1 square x2 plus 2x2 minus 4. So like we discussed earlier, we put x1 dot to be equal to 0 and x2 dot to be equal to 0 as well. Okay. So now with this two expressions, if x1 dot is equal to 0, then we simply write it to be equal to 0, and we find that this very expression, that x1 into 2 minus x2 is equal to 0. Okay. And then, if I can manage this. And then if you have x2 dot is equal to 0, so you put x1 square x2, and then you take x2 common here, and you get an expression of x2 in this one, which is equal to 4 by x1 square plus 2. So now what we do is we simply put the expression into this very equation. So we have x1 into 2 minus, instead of x2 we are substituting 4 by x1 square plus 2, and then solving it we get x1 to be equal to 0, and if you substitute back the value of x1 here in this very form, then we get x2 to be equal to 2. Okay, so our answers are simply x1 is equal to 0 and x2 is equal to 2. So based on this, the correct answer would be the fourth one, right? So, and you can actually check it back. So if you put x1 to be 0 here, you see that x1 dot is 0. And then if you put x1 0 and x2 to be 2, so 2 2s are 4 minus 4, and that means x2 dot is also equal to 0. That means if your states reach the position 0 comma 2, then it won't be moving anywhere further unless you're forcing it to move to some direction. Okay, it will just stay there for always. So that means this is an equilibrium point for the given system. Okay. I hope that's clear to everyone. Right. You can't comment on it right now. So you need to do further analysis to know whether it's a stable or unstable one. For a non-autonomous system, yeah. So maybe you can. So you want a practical example, or you are talking about like what can't you not visualize? That's what I want. Right. Yeah. So right now, so I'm not very sure what your doubt is. Okay. This is just a definition. And most of the systems that you see, for example, if you consider a mass spring damper system, that is an autonomous system. However, if you consider to the like the minute details, for example, where the damping coefficient can vary with time, the friction coefficient, for example, you can have a simple electrical circuit, okay, where you have a resistance, an inductance, and a capacitor, and the resistance would gradually, the value of it would change with time, because once you're operating it for a longer time, the temperature will affect the resistance value. So that means this very system, its parameter is actually time dependent. So when you're writing the dynamics, although we assume all those things not exist and we simply write V is equal to IR, but if you consider the dynamics, then you will see that the R can actually vary with time. It varies very slowly. That's why we approximate it to be an autonomous system, a simple system which doesn't depend on time. But it actually depends on time if you consider the dynamics over a longer horizon of period. Okay. So yeah, so that variation of the resistance, you can even get an expression like dRdt, how the resistance value changes. So that would be changing with time. So once you put it into the simple, if you put an RLC circuit, and just write V is equal to IRV. Your current can be one of the states, and your, say, rate of change of current can be another state. Or say the charge is one state, and then rate of change of charge, which is the current, that would be other state. So in this case, your resistance value can actually be explicitly dependent on time. So that would become a non-autonomous system. Okay. 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 So yeah, do we have any other doubts? Okay, so we will move on to the next question. Um, let's put it this way. Yeah, consider a system with origin as the equilibrium point. Which of the following solution trajectories is not asymptotically stable? So, is said that origin is the equilibrium point. That means you have only one state here. X is the only state. And if origin is the equilibrium point, that means X is equal to 0 is the equilibrium point of the system. Now, which of the following, the video seems to be blocked. Yeah. So, which of the following solution trajectories? That means they've given the solution how X would vary. Which of this is not asymptotically stable? So, like, how do we find out if something is asymptotically stable or not? Right. So, let's just go to the OneNote file. Yep. So by asymptotic stability, we mean what any idea what do we mean by asymptotic stability? You guys must have seen some graphs or curves. What do we mean by asymptotic? If something is asymptotically going to a point, it means it's going near to that point, although it's not reaching to that point, but it's always converging to that point. It's continuously moving towards that. So when we say something is stable, the origin is stable, that means we want the states to go to the origin's value, which is 0. And if we say that it is asymptotically stable, that means it's always converging towards the origin. But when will the state reach the origin? It will reach at t tends to infinity. That means after infinite time, is always gradually converging, and at some point of time it will reach there. Okay, so this can be my xt. This is just an example of I'm sorry about the internet is really slow here. Okay, so while it appears, yep, now it's appearing. So yes, like we start from some point, and then the trajectory would eventually, it eventually goes towards 0. When will it finally reach 0? It will finally reach 0 at t tends to infinity, and you don't know when that is, but is a theoretical way of saying that it will reach there at some point of time. So that's what we mean by asymptotic convergence. And further, if the equilibrium point is stable, then we say it's asymptotically stable. So a simple way to find out the answers is to check the limiting value of t tends to infinity x of t. If it is equal to 0, then we say that, well, it's an asymptotically converging, it's an asymptotically stable point. Okay, so I think it's quite easier to do for all you guys. Maybe I'll just show some of the examples. You can also help me. So we have here, see the first one. So we have a x of t naught. What is x of t naught? That means it's the value of x at time t equal to 0, which is the initial value. Okay, so this is some constant value. X of t naught is a constant value. Say x of t naught is equal to 10. Okay, so we have a into 10 square, which should be 100. So you have 100a minus e to the power t into x of t naught, which is again say 10, right? So now you see this is a constant term. It will not go to 0 even as t goes to infinity, right? And what about this one? You have e to the power t. Will it increase or decrease with time? Yeah, it will increase. So either of these terms here, none of this actually will go to 0. They both, one is constant and the other one is increasing, but with a minus sign. So it is increasing in the negative direction, right? But it will not go to 0. So turns out that limit t tends to infinity, your ax t naught square minus e to the power t x t naught is actually not going to 0. Okay. Now what about the next answer? We have x of t naught square minus 1 by t plus 1. Any idea about this? It can? Yeah, it can go to 0. And what's the way to do it? We can simply use L'Hospital's rule to say that, well, the upper terms are both zeros because x of t naught square minus 1. So if you differentiate it, it will be only 0, right? Because x of t naught is a constant, its square is a constant, minus 1 is a constant. So differentiating it will give you 0. And for t plus 1, so t will become 1 plus 0. I'm just using simple L'Hospital's rule, right? So this would become equal to 0. So this is then one of the correct answers. Internet is massively slow. But okay. So let's look at the next option. We have limit t tends to infinity. Yeah, e to the power minus t x of t naught plus a. Right. Now, can you tell me what would be the answer? How would a converge? For the second term, you have a constant a. Will it go to 0 at any point of time? Yeah, unless a is 0, there is no convergence. Although e to the power minus t will go to 0, it will the other term will not. So basically, then this is not going towards 0, so it will not be asymptotically stable. For the last option, we have e to the power minus 2t plus x of t naught square by 2t. So now you see in this case, the first one, e to the power minus 2t has a converging graph, and as t goes to infinity, it goes to 0. So this will be 0 plus limit t tends to infinity 0 by 2. Why 0 by 2? Because we have, by using L'Hospital's rule, we have this term to be differentiated to be 0 and this one will become only 2, right? So you again have 0. That means this curve is actually going towards 0 as t goes to infinity. This trajectory is going towards 0 as t goes to infinity. So we have the second answer to be correct and the fourth answer here to be correct. So these two are the correct options. Okay. Oh wait, sorry. The question was not asymptotically stable, yeah. So it would be the other two. Sorry. So yeah, the question is not asymptotically stable. I hope you all were careful while solving this. Okay. So we will now move on to the next question. So was this part clear regarding the fourth question? Okay. So yeah, we'll now move on to the fifth one. This is a very simple theoretical part. I think you guys have gone through the notes and noted it. For the system, x dot is equal to f of tx, which property is related to existence and uniqueness. So you can read actually Khalil's book. There is a book by Khalil. I'll just write down the name. Yeah. So it's a book called by Khalil. Let's see what the chapter is. Just a minute. I'll give the chapter and page number so that yeah, it's not syncing. So Khalil's book, section 3.2. So if you go through that, you can actually see that uh, the proof of it is given, although you don't need to know so much details just for going through this course. But yeah, so the answer to this would be the answer would be it should be piecewise continuous in time. Should be piecewise continuous in time and locally Lipschitz in X. Okay, so that what does it mean? Piecewise continuous in time means so there is no discontinuity over the time period. And locally Lipschitz in X is related to some definitions where you can find the solution of the trajectory, which would be like you would always be able to come up with a solution, and it would be a unique solution. There won't be any variations. We need this because we're dealing here with nonlinear systems, and there might arise cases where there is no solution at all, or there may be more than one solution. So how do you design a controller for such systems? So for this kind of problems, we first ensure that the solution or the trajectory is unique and it exists, and then we move on to design the controller. That's where this locally Lipschitz and piecewise continuous in time comes to use when you go for controller designing. So the next one is again quite simple. So your equilibrium point is given to be the origin for a system x dot equal to f of tx, and it is said that this is uniformly stable. What is meant by uniform stability? So first of all, stability is something that uh, if you look into only autonomous systems where there is no time dependence at all, okay, that means there is no explicit time dependence at all. In that case, we only talk about stability. uh, Unstable, there we have asymptotically stable, we have exponentially stable, we have globally exponentially stable, we have globally asymptotically stable. That's all the terms we have. Okay, now once you come to non-autonomous systems where your system dynamics, if you can see this one, okay, oh my god. So if you see the system dynamics, which is x dot equal to f of tx, we have a t component. That means it is okay, so it's a non-autonomous system, which means it is explicitly dependent on time because you have f to be a function of t and x. It's non-autonomous, right? So whenever this t thing appears in the dynamics, whenever it is non-autonomous, instead of simply talking about stability, asymptotically stable, globally asymptotically stable or exponentially stable, we have another definition which involves the word uniform. So we have stability, then we have uniformly stable. We have asymptotically stable, we also have uniformly asymptotically stable. We have exponential, well, exponential doesn't require the uniform idea. If you have globally asymptotically stable, you also have uniformly globally asymptotically stable. So what is this uniform thing? This uniform word that you see, it simply says that, well, since now your dynamics is explicitly time dependent, if something is uniformly stable, it will not depend on what time you are starting your dynamics. Okay, so your state is starting at certain time value. If I'm saying x dot is equal to x, it does not matter at what time your system is starting. Okay, because x dot is simply x, it will vary based on the value of the state x. Now if I say x dot is equal to x into t, So now it depends on at what time you're starting. If you're starting at t equal to 10, then x dot would be 10x. If you're starting at t equal to 50, then x dot would be, for the first time instant only, x dot would be now 50x, right? So it depends on the initial value or the initial time instant as well, only for non-autonomous system. So when we are saying uniformly something, that means this property is not time dependent. No matter when you start, he will always be stable. Okay, so we have this idea, therefore uniformly stable, right? So you can see out of the options. So mhm. So it's not independent of the initial value of the state directly, because of course whichever analysis you have, that will depend on what was x naught. But yeah, it is true that it will not depend on at what time you're starting. Okay, so even if you start now, say your x of t will be always less than equal to 5. This is a uniform boundedness expression irrespective of when you start. Even if you start at t equal to 10, your xt will always be less than equal to 5. Even if you start at t equal to 1000, your xt will be always then less than equal to 5. Okay, so it's not exactly independent of the initial uh, value of the state, is independent of the definition is independent of the initial time value. Okay, why? Because see, if you are starting from 1000, you may start from x not equal to 1000 at any time. But if you're starting from 1000, you will require some amount of time to go to 0, right? Now if you start from 5, for the same dynamics you might reach to 0 at a very earliest time, right? You will need less time to go to 0, whereas if you start from 1000 you will require a lot of time. But it doesn't say that, well, when you have to start. It doesn't say that, oh, I'm starting from x not equal to 1000 at t equal to 2 o'clock, so I will reach there at 5 o'clock. Now if I'm starting at x not equal to 1000 at t equal to 5 o'clock, I will reach there at 5:30. This is not guaranteed. Okay, what is saying that if you start at 2, you will reach there at 5. If you start at 5, you will reach there at 8. So the performance is uniform. The performance is same irrespective of when you start. Okay, I hope I could explain. Yes, asymptotic convergence means the, yeah. So asymptotic stability means the system is stable and asymptotically convergence. Okay. First of all, your origin should be stable. That's fine. And then your dynamics should be convergent as well. Let me give you an example if I can. Just a minute to check it. So there are things where you have your origin to be stable but not convergent. There are trajectories where you have the origin to be convergent, or sorry, the state to be convergent to some place, but it is not stable. Okay, so let me see if I can get the examples. Yeah, so okay, this would take a long. Do you have any idea of nonlinear control in general? I'm just asking, like, it would help me explain better. Okay, so I hope you've heard about limit cycles. Let me see if I can go through that. Yeah. So what happens in limit cycles are that, I hope you can see the PDF. Yeah, this was one of the example questions. So you see, this is a limit cycle where this trajectory that you see, this is the limit cycle trajectory. That means if you start inside the limit cycle trajectory, you will always stay in that very box. So of course, it's not as the origin is not stable because you are never going to the origin, right? But the trajectories are bounded. You don't go beyond a certain region. Okay, and they would always converge towards this boundary or whichever is the trajectory of the limit cycle. Now, if you start from this point, say you start inside the circle, then you go around, reach to this larger elliptical region, and then you again go back inside the circle. Then you again come out, and you again reach to the boundary of this elliptical region, and then you come here. So basically, you see your trajectory. If it starts inside the circle, it will eventually go around and come to the center, which is the origin. So it is eventually converging, right? It is coming there, right? But it's not, you can't say it to be exactly stable. And then there are cases where the trajectories are stable. That means, say if you, let me see if I have. So for example, stability can mean that, let me draw it, that would be better. So you start in this boundary region, and then your trajectory keeps behaving in this way. I don't know if it's visible at all. Yeah, so it will take some time to appear. It just means that your trajectory, suppose there is a boundary, and then your state starts from here and it eventually keeps oscillating. Okay, so you are reaching near to the origin and you are staying nearby it. So for that delta ball where you start, you have an epsilon ball inside which you will always stay, which is the basic definition of stability. So for a given delta ball where your x naught will lie, your the final state trajectory will always lie inside an epsilon ball, which is a small area around the delta ball. So you see, it will always lie near to that point, and that means it is stable. However, it's not converging to any point. It keeps oscillating, right? Because oscillating, there is no convergence. So basically, there can appear situations where the origin is stable, but there is no guaranteed convergence. There can appear situations where the trajectories are convergent to some point, but it may not converge towards the origin. So that means it's converging, but it's the origin is not converging to the origin. So there is convergence guaranteed, but not stability. Now, asymptotic convergence simply means that the trajectory will reach to zero or will reach to the infinite, the origin value at t tends to infinity. It will eventually reach to the origin. That is your asymptotic convergence. Now, provided your origin is also stable, then instead of saying that the origin is stable and asymptotically convergent, we say that it is asymptotically stable. That's it. It's just the combination of the two terms put together. Okay. Yeah. Yes, yes. Because whatever equilibrium, say your equilibrium point, we saw in the first example, it was 0, comma 2, right? We saw an example. Yeah, this one. We had the equilibrium point to be 0, comma 2, right? This is not the origin. However, if you put, say, x, okay, I'm writing in a measurable way. Say x is equal to x2 minus 2. Say x dash is equal to x2 minus 2. And now if I say that, well, my states are x1 and x dash. So if x2 is equal to 2, your x dash is equal to actually 0, right? So you can always shift the system dynamics and bring the equilibrium point to the origin, which would be 0, comma 0. Okay, so origin uh, by saying origin, it means that the equilibrium point has been shifted to the origin by doing some transposition or translation in the dynamics. I hope that's clear. Okay. So we'll move on to the next question. Yeah. So yeah. So the like we said, the equilibrium point, which is x equal to 0. This is a non-autonomous system. So we have the notion of uniformity here. This is uniformly stable if. So the answer is for every. Let me see. Where is the ball? So for every epsilon greater than 0, there should exist a delta epsilon greater than 0, such that x of t naught. This is the correct question. I have which week is it? Um, oh yes, okay, yeah. So for every epsilon that is greater than 0, you will have a delta epsilon which is greater than 0, such that if your initial state starts within the delta ball, your trajectory will eventually go around but always stay within the epsilon ball. Okay, so if you look at the answer, is simply saying that, well, say you have this, I don't know, you have this, so this is your delta ball, okay, and then you can have another epsilon ball around it. And it simply means that if you start inside the delta ball, no matter what you do, for all time you will always stay inside the epsilon ball. Okay, that is basically the notion of uniform stability. So no, it's irrespective of where from you start, but if you start inside this, you will always stay inside the larger ball. Okay, but and if you notice the options that were given to you, so either this one or this one is valid, right? But out of this two, you see in this one delta of epsilon. So delta is the region from which your initial state will start. And in this case, it depends on T naught. However, if it is uniform, it should not depend on the value of T naught. So this is your correct answer. Means for every epsilon greater than 0, there would exist a delta, which is a function of epsilon, not of T naught, such that if it starts in delta, it will always stay in the epsilon ball. Okay. So now we move on to the next question. How much time do we have? Okay, we have 1 hour. So yeah, the sure. Mm-hmm. Yeah. So this one was due already, right? It was due. So you can kind of you have time to submit it, but it's not like I'm not going to solve like everything. You have to still go through the details. Yeah, yeah. I'll not be solving all the questions for you. Yeah. I hope that's clear. Okay, okay, yeah. So it's not, I'll not be actually going through the last questions, which requires you to go through the details on your own. Okay. So the idea of this is that I will be just explaining to you the, some of the questions and the basic things. So for the first assignment, you need some idea to kickstart and then solve your problems. And then eventually you will become an expert in solving it on your own. So it won't be a problem anymore after that. Okay. and then we can actually go through other kind of problems as well if we want. So, but well, if you guys are interested, I can actually skip going through this, maybe talk about the details. So, okay, yeah, that can also be fine if you want. So, okay, I will leave this for you then to completely do it on your own. I hope it's understandable. So, for the Lyapunov function we are talking about here, so is this a autonomous or a non-autonomous system? Any idea? Yeah, it's a non-autonomous system. And then if you have to talk about the stability, you can see we have many options here, like stability. We have then uniform stability. We have then unstable, locally stable. You can also have options like asymptotic stable. Then you have uniform asymptotic stable, globally stable, and uniformly globally asymptotically stable. Right. So, um, what idea do you have about? So maybe you can tell me how can we check for asymptotic stability by using Lyapunov analysis? What's the idea to do that? Okay. And what? Okay. So, okay. Okay. So, how do we? What if you don't get your v dot to be less than zero at the very first step? That's the idea to do it. So usually say your function is, v equal to some x1 square by 2 plus x2 square by 2. And then your v dot, if you solve it, once you solve v dot, you actually have to replace the dynamics of x1 dot and x2 dot. Because v dot will have x1 dot plus x2 dot. So in that case, there might appear situations where once you replace it, you do not get v dot to be less than 0. You get v dot to be less than equal to 0. Okay. So what do we use then to show whether to check whether the autonomous system is asymptotically stable or not? Right, but can we check asymptotic stability in that case? Okay, anybody else? I think there were two other people, right? So did you hear about this thing called Lassalle's principle? Okay, so Lassalle's is how you actually go for checking whether your system states are the origin is asymptotically stable or not. So we have this principle called Lassalle's principle. Now this is only applicable to the autonomous setting. What if your system is now non-autonomous? How do you do it in that case? Mhm. Yeah. You can write the same Lyapunov function. No, not necessary. Yeah, there is no such requirement. So I will actually, so we have one last example. I thought I will show it to you guys. I was going to do this briefly, but you can see here W is a time varying quantity, right? W is dependent on time. W is just some other signal, and it is showing to be L infinity, which means the signal is bounded. Now, is this an autonomous or a non-autonomous setup? Oh, it's not being shown. Okay. Oh, sorry. I see, I see. Okay, just a minute. Forgot I moved. Is it visible now? Okay. So in this question, what about WT? WT is time varying. You don't know whether WT is an explicit function of time or WT might be a constant. We have no idea. So this can be an autonomous system. This might also be a non-autonomous system as well, right? Because you don't know what is the expression of WT, right? So maybe what I will do is I'll just show you how to apply Lassalle's to this example, provided WT is a constant term, and then you guys can try and solve it for WT not being a constant term. That means which would be the answer to this very given question. You can see here W is time dependent. So what if W is not time dependent, right? So that would give you an idea of Lassalle's. So what was the example? Yeah. So we have x1 dot equal to minus x1 plus x2 w, and x2 dot is equal to minus x1 w. Given w is constant. So anyways, while it appears, let me just write. So it's the same dynamics. We can just consider v to be equal to x1 square plus x2 square by 2. So you have v to be, okay, it appeared x1 square plus x2 square by 2. And then your v dot is equal to x1 dot plus x2 dot, right? So if uh, let's just wait. So I'll just continue till it appears. So basically, this is the dynamics. I'm taking v to be x1 square by 2 and plus x2 square by 2. So if I differentiate v with respect to time, I have v dot, which is, okay, it came x1 dot plus x2 dot. And then if I replace the dynamics here, I have minus x1 plus x2w plus x2 into minus x1w, which would be simply minus x1 square, right? And then this is, so now you can tell me where it appears. So if v dot, v is a function of x1 and x2, right? That means if I have to say that v dot is negative definite or less than 0, then v dot should also be a function of x1 and x2. But we see here that v dot appears only in terms of x1, right? So v dot is equal to minus x1 square. That means this is negative semi-definite. I hope it's clear. Can you guys tell me the definition of negative definite? Why? Okay. Uh-huh. Right. So what's the definition of if I say V dot is negative definite? What do I mean? It means that V dot is less than 0 everywhere, right? And V dot of 0 comma 0 should be equal to 0, right? So let me just write it down. So only when x1, x2 are both 0, we should have the function's value to be 0. And other than that, everywhere else, the function should be negative, right? But here if you see, V dot of 0 comma 1 is also less than 0. V dot of 0 comma, so not, let's not write less than 0, it is equal to 0 in fact. Is equal to 0, right? And then V dot of 0 comma 2 is also equal to 0. Simple. So basically, it is not that for any other value of x1, x2, only at 0 comma 0 it should be 0. Elsewhere, everywhere else it should be less than 0. So that means here this is not true, right? Because v dot of 0 comma 1 is also 0, which should not be the case. It should be less than 0. So therefore v dot is a negative semi-definite function. Okay, and if it's a negative semi-definite function, the best we can conclude is that right now what can we say about the equilibrium point of the system? Is it, what is it? Is stable, unstable? Uh, right, but we are saying that v dot is less than equal to 0, right? It is negative semi-definite. Yeah, then it is stable. So 0 comma 0, therefore 0 comma 0 is stable. That is for sure. Okay. Only autonomous. Right. Yeah. Mm-hmm. Yeah. So that goes you to solving the question. So for non-autonomous system, I think sir has gone through it in lecture 2, that you will find Barbalet's lemma first of all, and then you will also require something called Lyapunov-like lemma. So it's not a Lyapunov theorem, but it's Lyapunov-like lemma, right? So if you use that, then you can actually conclude about the system's convergence properties. So this example is still continuing actually. So we have 0 comma 0 to be stable. Now if we continue to use Lassalle's principle in this one, then we have v dot to be identically equal to 0, right? That should be the case. If for invariance you need to be always at the 0. So okay, it's not. Yeah, so we have x1 square to be equal to 0, identically equal to 0, which implies x1 to be equal to 0, x1 dot is therefore 0, and if x1 dot is 0, then we know x2 dot, which is equal to minus x1w, is equal to 0. Right? That is how you use the Lassalle's principle. So therefore 0 comma 0 is asymptotically stable. Wait till it appears. Yeah, so we had this for Lassalle's, what we do is we equate v dot to be identical equal to 0, and then we see that well, x1 is equal to 0, so that means x1 dot would be 0, and if x1 dot is 0, then so it is identical equal to, so this triple sign actually means identical equal, which means it is 0 for all time. And if it is 0 for all time, then it means x1 dot would be 0, and therefore x2 dot, which is equal to minus x1w given from here, right? Then this is also equal to 0. equal to 0. Yeah, right, right. Because that's what you want for asymptotic stability, right? It's an invariance principle. That means if you start from 0, you will always stay at 0. So if you're, what do you mean by starting from 0? That means your v dot should be identically equal to 0. That means what is v dot? Basically, v is like an energy function, right? So v dot is the rate of change of this energy function. So if something is identically equal to 0, that means it is 0 at all time, which means your rate of change of energy is 0 constantly, which means the energy is not changing. And if the energy is not changing, that's the point you want to find for stability analysis, right? So if you are going there, it should be, is all time 0 means it has converged to that 0 point already. It's not going to change any further. It can start from anywhere, but you want to find the point such that if it reaches 0, then it will not change any further. So that's why you are putting that, well, what is my x2 or what should be my x2, so that if I go there, it doesn't, if I reach that very state, then my v dot will always stay 0 after that time. So it would be invariant, it won't be changing any further. So that's why we do it like a back calculation. So if my v dot has to be identically 0, yeah, then what? Right, because yeah, because that's the invariance thing saying that your energy should not be changing any further. So is not exactly opposite. Is like, since you started from v, then you found v dot, and after that you could not conclude what happens to x2. You have nothing else to conclude from this expression here. So now you start playing with v dot, because that's where you ended, right, with Lyapunov. So now you start playing with v dot and see, well, what further can I learn from v dot? And so following LaSalle, we just learned that, well, my x2 will also be equal to 0 if these are identically 0. So if these are identically 0, then x2 is also identically 0. That means if I reach 0, 0, I will stay at 0, 0 for all time. Okay. Which is the idea of asymptotic stability. Like, you have already reached there and you're staying there. So that gives you the asymptotic stability. Okay. Okay. Yes. So, in fact, we can actually conclude further about it. So you see that V is positive definite and is radially unbounded. So any idea what we mean by radially unbounded? Okay. Yeah. So it's basically, just a minute. Okay. Yeah. So I don't know why this tab got closed now. But I admitted them to the call. Okay, admit all. Yeah. So where were we? So yeah, it's radially unbounded. It just means that suppose you have this x1 square plus x2 square, which is a function that looks like a kind of a parabola, right, in 3D. So basically, as your x1, x2 increases, it keeps on increasing and it goes towards infinity. So if x1, x2 goes to infinity, the function will go to infinity as well. So that's a radially unbounded function. So if you have gone through the courses, you would notice that provided your V is positive definite and it is also radially unbounded, right, then you can actually say that V is, sorry, can say that the origin is globally asymptotically stable. So why globally? Because right now, wherever your states keep spreading, your V also keeps spreading and it keeps increasing. So it brings in the notion of globality in that case. Okay. Along with that, your domain should also, that means x1, x2 should be the whole uh, real space. That means x1, x2 can take any possible real value, which is true in our case for x1 square plus x2 square. Whatever value you put of x1, x2, if you keep increasing it, your V will also keep increasing, right? So that is the idea about the function being radially unbounded, and if it is the case, then along with asymptotic stability, you can also comment on 0, 0 being globally asymptotically stable. But this was using Lassalle's principle, and if you notice that we have it only for this example where W is constant, right? But in this very question that has been given to you here, W is time varying. So now you can't use Lasalle anymore. And what you have to do is you have to go through Lyapunov-like lemma, and along which includes the Barbalet's lemma itself. So if you can show that it satisfies the conditions of Lyapunov-like lemma, what are those conditions? You consider a simple Lyapunov function, and then first you have to ensure that your function v is lower bounded. Okay, that means if say this is your v function, there should be something below it, something that bounds it. It doesn't keep going towards minus infinity. Then you have to show that v dot is negative semi-definite, which was true for this case as well, and that v dot is uniformly continuous. So what do you mean by uniformly continuous? It means whichever region you pick, it's continuous in that region as well. Okay, and there's a way to check uniformly continuity, which is using the Barbalet's lemma. So just to give an idea, if W is time varying, then we cannot apply Lasalle. Right? So we rather go for Lyapunov-like lemma. Sitting invisible long. Yeah. So it takes a lot of time to appear. If W is time varying, then we cannot apply Lassalle's invariance principle. So we'll go for the Lyapunov-like lemma. And what does it say? You start again with the same V. Choose V to be positive definite function. PD means positive definite. Okay, so you choose V to be positive definite, and then you have V of x comma t is lower bounded. And next your V dot should be less than equal to 0, and then your V dot is uniformly continuous. So what's the way to check if something is uniformly continuous or not? So this is true if and only if let me not write if and only if. So can say that this is implied Where does it take? Yeah. So this is this uniformly continuous. How do you find out uniformly continuous? You have to ensure that v double dot is actually belonging to L infinity. That means it's bounded. That's given by Barbalet's lemma. So which you will get at the end of lecture 2, I think. So if these two are true, then if 1, 2, 3 are satisfied, then your v dot is equal to 0 as t tends to infinity. Let me write it as limit t tends to infinity, v dot is equal to 0. Yeah. So provided these three conditions are satisfied, which is not Lyapunov's condition, but is similar to that, and you can apply simple calculus logic, then you can actually see that if these are satisfied, then your limiting value of v dot will eventually go to 0. That means it would be, which is same as saying that if v dot is going to 0, then the states inside would also go to 0. Then you can actually apply the same logic of v dot being identically equal to 0 and find about these states by doing the analysis in the opposite way. So this is something that you have to use to prove for this very example. So to prove for this very question, to find out the stability of this very equilibrium point. Okay. And yeah, so question number 10 is regarding okay, so uniformly continuous means that is continuous at all time instance, right? If you're whichever small segment you take, it's continuous there as well. If you take even a smaller segment, you will still find continuity there, which means your right limit and left limit are equal and is equal to the point. So I think we have done it in classes earlier, I think class 10 or 11 maybe. But the unit, yeah, the right hand limit and the left hand limit. And in addition to, maybe I can give you an example or a picture. Let me see. So yeah, while I find this, let me just explain these things to you first. So for the last question, I think sir would be moving towards designing MRAC, which is the Model Reference Adaptive Control, in the next classes. And for that, you have to actually need to find out how to match, sorry, how do we match a reference model with a given plant model. So this is a very simple question. You have to see what values these parameters. What are the parameters here? MM, BM, KM, R, and here B and K. These five are the parameters. R is an input signal, which is the reference input, and F is also another input signal, right? So you have to just ensure that the models match. So what should be the values of the parameters for the models to match? Okay, let me see uniform continuity. Maybe I will share the screen with you. Easier. Yeah. So I hope it's visible. Is it visible to you guys? Yeah, you can see. So what do we mean by this? Is first a simple example of continuity, right? Like you already said. So here x naught and f is the function of x. So this is a point given to you x naught. Now continuity means its left hand limit, which is this point, and its right hand limit, and the value of f of x naught. This all should be equal. That's your continuity's simple definition. Now there is also another definition considering epsilon delta. So what it means is that if you take a small epsilon segment, like a very small segment in this part, and you expand it and you like project it onto the curve f of x. So this is the region that you get, right? So for all epsilon greater than 0, so no matter what is your epsilon value, you can always find a delta value, which is this smaller part. Delta is the region where x will vary, epsilon is the region where f of x is varying. Okay, such that x minus x naught would be less than delta, implying f of x minus x naught would be less than f. What it simply means is that, um, so if you choose any epsilon region, you project it onto the curve and then project it back onto this very plane. Okay, and you onto this very line, and you will find that, so for any x, if you take any x inside this small delta region, and then you find x minus x naught, because x naught is the center of this line. I hope you understand. So x minus x naught, this value, if it is less than delta, then the corresponding f of x minus f of x naught would also lie within the epsilon region. That's the like a different way of saying continuity defined, which in other words means that if it is not continuous, you will actually see that even if your x minus x naught is less than delta, your f of x minus your f of x naught will not be less than epsilon. Okay, because for example, say if this line is coming till here and there is a break and it starts from here. Okay, so maybe I can draw it somewhere for you. Let's think. Yeah, okay. So you see for this given example, say here is a discontinuity, right? And you find out this, like you pick this value to be your x naught. Now you can choose any epsilon. I'm choosing this to be my epsilon region. Okay, so even if you pick a delta region around x naught, okay, centering x naught, you find a delta uh, diameter region or a delta length region, and whatever value of x you choose, for all values you will see that x minus x naught. So this is the x you pick, this orange one, although you can't see it. Okay, just a minute. Yeah, so this is the x you pick. Okay, now your x minus x naught is of course lying within delta, but you see your f of x, which is here, and f of x naught is here, right? If you choose this value, if you consider it to be left continuous, or if in fact you can put your x naught to be in this segment a bit aside to this very point. So you will see that your f of x minus f of x naught, this is not lying within the epsilon ball. Okay, so that means it's a different way of saying that basically your given curve is not continuous at x naught. Okay, you can choose your, this drawing is not very good. You can choose your epsilon to be smaller, and you will see that this minus this difference, this doesn't lie within epsilon region. Okay, so that goes regarding yeah, yeah. So that is simple continuity definition that we have. Okay. Mm-hmm. Some delta. Yeah, right. Mm-hmm. So these two are not the same, right? One is one is stability definition. The stability definition is with respect to certain dynamics, and this is a different epsilon delta argument. Okay, because this is where you don't have, yeah, right, you don't have any dynamics here right now. You just have some f of x as a function, and we are talking about the continuity definition in terms of epsilon delta. Okay, and so for, you're right, there should be a delta which depends on epsilon. Right. So if we go to continuity in an interval, you don't need all these definitions. So let me just move aside. So wherever you want to draw your epsilon, you will see if it's continuous, you can always find a delta region. Okay. So basically, hmm hmm right, right. Because the function is given to you, and now you have to test whether it is continuous or not. So fx is given to you already. Yeah. So you can carry on the analysis. Right, right. You just have to check whether there is a delta or not. So it depends. If you see here, if your x naught is this very point, right? That means you want to find the continuity at this very particular dot. Then you're based on the curve or based on the fx function, your delta is very small, right? Now, if you have to for a given constant epsilon itself, your delta is small. Now, if you are coming in this less slopey region, if your x naught is here, if you for the same epsilon, if you draw a delta, if you like project the vertical lines delta line, then you will see that the delta has increased in size. If you further for the same epsilon, if you need to find continuity at this point, this is your x naught, then you see now your delta is larger in size, right? Yeah, so delta is, in this kind of cases, delta is dependent on epsilon as well as x naught. So at what point you are finding the continuity, that also matters, right? So when we talk about uniform continuity, we would want this delta to be independent of x naught. We don't want to know. So at what point I'm finding, at what point I'm checking the continuity, I'm not interested in that, and it should be like irrespective of this very x naught value. Okay. Yeah. So like if you see here, so it is given that that means for all epsilon. So it's a continuity in an interval. So you are taking some interval, right? For this region, for this region, for this region. So for all epsilon greater than 0, say you fix the epsilon. And then for all x naught in that interval, there will exist a delta. Okay. So based on your interval, whichever interval you're picking, your delta is also actually changing. There will exist a delta, but your delta is changing based on x naught value. But in this definition, when we talk about uniform continuity, it's actually flipped. Now we are saying that for all epsilon greater than 0, where you are giving a certain epsilon region, epsilon strip length, there would exist a delta which depends on this epsilon, which is greater than 0. And then for all x naught in that interval, so now x naught is depending on a given interval, but your delta is not dependent on the value of x naught anymore. Okay. Yeah. So yeah, so it's just saying that it's not exactly the same drawing for this one. So if you go for such functions, for even for the Lyapunov function, if you the given function that we consider x1 square plus x2 square, if you check it, you will actually find that once you find v dot is uniformly continuous. So if you plot v dot, you will see that your delta doesn't have to depend on what value of x1 or where you're checking the continuity. Okay, so I'm referring to the example that we were doing. Yeah, so this very example which was given in the question with w being time varying. So if you solve this question, you will then see that your V dot is actually, I think it turns out to be uniformly continuous. Yeah, your V dot is uniformly continuous. So then if you plot it, you can see that your epsilon, the delta, it doesn't have to depend on at what value you're checking the continuity. Okay. Yeah. Hmm. L infinity. Yeah. Of this, right. Of this very signal, whatever is given to you. Yeah. Mm-hmm. या पुन्हा black lemma. Uh-huh. Yeah, so the third condition, you don't have to check, like if you, one way is that you just ensure that V dot is uniformly continuous. Okay. But how do you prove it? If you can prove it directly, very good. It's really excellent. But the other way to do it is that will you go for Barbalet's lemma. And Barbalet's lemma tells you that if V double dot belongs to L infinity, then V dot is uniformly continuous. It's a reverse way. So if you can prove this, then this third condition is guaranteed. Okay. That means you will check condition 1, condition 2, then you will check whether V double dot belongs to L infinity or not. If it is bounded, that means if it belongs to L infinity, then this means V dot is uniformly continuous. Okay. X1 and X2. Yeah. You can have a function of time as well, is up to you. Yeah. Okay. Okay. So I think you guys can do these questions. This is simple matching the conditions. You have to match the two models. What should be the values of the parameters? So this this very given plant model is same as the reference model. And L2 norm you can find directly from the definition. I think it's already explained in the class. And yeah, that's it. So for this very question, for the question number 7, there was some other ideas about this, about a function being decrescent. I'll not go through this, but I think you guys can read this on your own. You will be requiring this logics. So first you will check for stability. Then you also need V to be decrescent in order to, other than being positive definite, it should be decrescent, whether it is radially unbounded or not. Doesn't show. Yeah. If V given V function, if this is positive definite and V dot is less than equal to 0, what do you mean by V being positive definite? It means V of t comma 0 should be 0 for all t, and V of t comma x would be greater than equal to W1 of x, where let me write it first. So I just want to go through the fact that if you have an autonomous system, that means if Lyapunov function is basically dependent only on the states, then doing the analysis is quite easy, right? But if your Lyapunov function needs to be time dependent as well, which happens in case of the non-autonomous systems, then what do you do? How do you define whether a function is positive definite or not? So to ensure that v is positive definite, you have to check that v of t comma 0 should be 0 for all t. Okay, so you don't, right now you don't worry about t, and then the definition remains the same, and then v of t comma x should be greater than equal to w1 of x. So what is w1 of x? W1 of x is another positive definite function. Okay, so for example, if v is equal to say x1 square plus tx2 square, let me write. Then you can choose w1 to be say x1 square plus x2 square. Yeah. So if v is equal to x1 square plus 1 plus e to the power minus t x2 square. Okay. So see, e to the power minus t, it can start from, if t equals to 0, then it would start from 1, and then as t goes to infinity, it go to a 0, right? So you can actually lower bound this function v using a function w1, which is equal to x1 square plus x2 square. Right. If you plot these functions, you will see that x1 square plus x2 square, that is w1, will always lie below v. So v is therefore greater than equal to w1. Okay. And if your v is greater than 0 and your v dot is less than equal to 0. So now we have checked that v is greater than 0, right? Because we have a w1 which is lower bounding v, and v of t comma 0 is equal to 0. So if v is greater than 0 and v dot is less than equal to 0, then you say that the origin is stable. Okay. Now what about going to, so yeah, let me just also mention this. W1 is greater than 0, W1 is continuous, and what's not required, okay. And W1 should be continuous as well. Okay. Now if so now this is for stability. If we have to talk about uniform stability, what we do is that, well, we need to ensure that v of t comma x is also decrescent. What is decrescent? Decrescent means, like we had v to be greater than equal to w1x, now we need v to be less than equal to some function w2x. Okay, so if you see here, e to the power minus t can vary from 0 to 1. That's its maximum limit. So it is lower bounded by the 0 value. And if I put, so my w2, if I choose it to be x1 square plus 2x2 square, that means here I'm putting the maximum value of e to the power minus t, which is 1. So then my v of tx will always be less than equal to w2x, right? If I put here 1, 1 plus 1 is 2, so x1 square plus 2x2 square. And this w2x is continuous because it is x1 square plus 2x2 square, and it is also positive definite. So that means v of tx is a decrescent function. Okay, in that case we say that the origin is uniformly stable. So this is an added condition. Further, right? It is further. If this is true, then the origin is uniformly stable. Further, if W1, I think, is radially unbounded, let me write this condition. Wait. So this is a further. Okay, this is an added condition. First, if this is true, then of course the origin is stable. Along with that, if your V is decrescent, it's a further thing. Okay, then your origin is uniformly stable, right? And then along with that, say also, or I can write further along with that. If V is greater than 0, V dot is less than 0, where V is less than W2 and V is greater than W1, then you have uniform asymptotic stability. So the asymptotic part appears because now you have V dot to be less than 0. So if it is less than equal to 0, then stability. Less than equal to 0 along with decrescence, then you have uniform stability. If there is less than 0 and decrescence, then it is uniform asymptotic stability. Okay, it doesn't appear, yeah. So V is now bounded by W1 and W2, and V dot is less than 0. Then you have uniform asymptotic stability. And finally, if all these conditions are satisfied, but now W1 is, say, radially unbounded, okay, and your domain is the whole Rn, then you have uniform globally asymptotic stability. So that means global because radially unbounded function. So wherever you go, the property of V and V dot would be satisfied. So you have, it's not appearing. But okay, you guys get it right. If W1 is radially unbounded and V dot is less than 0, V is greater than 0, V is between W1 and W2, so on and so forth, and then this is a uniformly globally asymptotically stable. So based on this, I think you can, although the global thing is not required in this question, but you can answer this now, right? So I think, yeah, that's all for today. If you have any doubt, you can ask. Are there any doubts? Okay, so there are other two participants. Do you have anything to ask? Okay, okay. So I think we can end the session here. And for the next course will be, if you guys have any questions, you can always post it in the discussion forum. I think you guys know where the discussion forum is. So there is this, let me just show it to you. I don't know if I can access it. No, it's not available to me. Okay, yeah. So you have this Q&A here. So if you all have any doubts, you can just post your questions in Q&A in this very forum, and then I will be replying to you hopefully within 3 to 4 working days. So that's all I have to say. So if you don't have any other doubts, so we'll just end the session here. Okay. Thank you all. Okay. Have a nice day.